Want to live longer? Maintaining muscle isn't just about performance or looks, it's about survival. Your muscles might stop responding positively to protein and exercise as you age or gain weight. It's something called anabolic resistance, and it's not just about getting weaker. Muscle loss is one of the strongest predictors of death, more so even than fat or many chronic diseases. Obesity and aging trigger inflammation and insulin resistance, blocking protein synthesis in your muscles and speeding up muscle breakdown. But there's hope. Resistance training, high-quality protein, and anti-inflammatory nutrients like omega-3s can reverse this. Anabolic resistance isn't a life sentence, but it does require action. This is Lecture 112 of the Metabolic Classroom. Looking to improve your own metabolic health? Visit insuliniq.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more. This is the Metabolic Classroom. I'm Ben Bikman, biomedical scientist and professor of cell biology. Today, we are discussing a concept that sits at the intersection of aging, metabolism, and muscle health: anabolic resistance. This term refers to the diminished ability of skeletal muscle to respond to anabolic stimuli. This is things like dietary protein and resistance training. It is a phenomenon that becomes increasingly relevant with age and even with obesity, somewhat regardless of age. And it plays a central role in the development of muscle wasting. That's a process called sarcopenia. Now, why does this matter? Muscle mass and strength are more than just markers of fitness. It's more than just looking good in the mirror. They are among the strongest predictors of longevity, actually. For example, large cohort studies, like those from the Health, Aging, and Body Composition Study, have shown that individuals with sarcopenia, that muscle wasting that happens with aging and chronic disease, face a 20 to 30% higher risk of all-cause mortality compared to those with healthy muscle mass. Just to put that in perspective, that kind of number blows other things like LDL cholesterol out of the water. So this is a marker that really appears to matter if you're concerned about longevity. Sarcopenia, with that idea in mind, increases the risk of falls and fractures, but it also increases metabolic problems like insulin resistance. After all, muscle is the great consumer of blood glucose, and the less muscle you have, the harder time you're going to have controlling your blood glucose, which in turn is going to keep your insulin high, thereby promoting insulin resistance. But think about all of this in real life. An older adult who loses muscle might struggle with simple tasks like getting out of a chair, leading to an increased dependence. So they need to have a lot of in-home help or even getting out of their home and into a care facility. And that actually leads to a cascade of other health issues. In my own research and teaching, I've seen students and colleagues, scientists, overlook muscle health until it really affects their daily lives. So we need to consider muscle as a foundation to vitality and long-term health. Now, before we dive deeper, let's just set the stage with what anabolic resistance actually means. The term refers to the blunted muscle protein synthesis response to stimuli that would normally promote muscle growth. In younger individuals, a modest dose of protein or modest resistance training can stimulate muscle protein synthesis effectively. But in older adults, the same stimulus often fails to produce a comparable response. This impaired response is more than just some consequence of aging, but rather it is an active, even multifactorial process that, as you'll see as we review the evidence, involves not only some dramatic shifts in hormones, also compromised delivery of nutrients to the muscle, some degree of inflammation affecting the muscle directly, and more. But with regards to, say, hormone shifts, some of these would include a declining level of testosterone that reduce muscles' sensitivity to growth signals, while impaired nutrient delivery could stem from reduced blood flow to muscles. The term anabolic resistance itself, just by way of some interesting scientific history, emerged in the early 2000s within the gerontology research sphere. And it was pioneered by scientists and even a friend and acquaintance of mine, Dr. Stuart Phillips. And it was his work and some others who highlighted how aging muscles require stronger stimuli to trigger growth. So imagine that this is sort of like a rusty lock. In youth, a gentle turn of the lock can open it. You don't need much force. You don't need much push. But with age, you need a bigger key, or you need more of a crank. You need more force in order to get that same action. But it is not, as I said, just limited to the elderly. Obesity, even in younger individuals, can induce some similar resistance to these anabolic signals. All right, with that as information, with the foundation now, let's explore some of the drivers behind anabolic resistance. And I want to submit that there are two major contributors to anabolic resistance. They're not the same: aging and obesity. Aging brings with it a decline in anabolic hormones. And remember, anabolic simply means building something up. So, and beyond the anabolic hormones, we have reduced amino acid delivery and impaired intracellular signaling. Obesity, on the other hand, is promoting things like insulin resistance and chronic inflammation, largely through the hypertrophy, the expansion of the individual adipocytes or fat cells. So let me just make that point clear. It's not a matter of fat mass, but more specifically a matter of the size of the fat cells that matters most. Now, these conditions overlap, which can compound the problem and accelerate muscle loss even more. But let's look, before we even go further into anabolic resistance, to just make sure that we have a common understanding of just even how muscle itself is maintained. Because like all tissues of the body, there is this constant remodeling. For example, you think about strong, healthy bones. That's just not a matter of pulling in calcium and locking it in. That actually leads to problems. In fact, some of the most touted medications used for osteoporosis or bone loss indirectly can promote selective bone loss itself, where the person is locking in the bone in a static state, which actually ends up degrading the bone more rapidly. So to say that all another way, or more succinctly, muscle needs to be turning over for it to be healthy. Muscle protein synthesis is a part of course, the first part of this equation, where new proteins are built within the muscle by pulling in the amino acids and then having the stimulus to lock them all together as a protein. And then we also have the exit, which is proteolysis, where old or damaged proteins are broken down. When synthesis exceeds breakdown, we have an increase in muscle mass. When breakdown dominates, then of course we lose muscle mass. But when the two are balanced, or slightly in favor, then we of course have some growth, and at a minimum, healthy muscle mass would be maintained. So let's just make this really, really clear and walk through a typical day when it comes to muscle remodeling. In the morning, you would have woken up in a catabolic state. You'd have relatively more breakdown happening than building up. But let's say you have a protein-rich breakfast. You have some amino acids flooding into the bloodstream, triggering synthesis to repair the overnight catabolism. By midday, we're active. Let's say we're walking, or even better, we're engaging in some resistance training or lifting weights or lifting ourselves with calisthenics. Then we have that mechanical signal, which is going to boost the activation of a protein called mTOR. And mTOR is critical. I'll revisit that topic and that protein in just a second. But suffice to say, the mechanical stimulus of any kind of physical activity is going to help with this growth signal. But in the evening, we're sedentary, we're fasting between some meals, we might start to ramp up some breakdown again. But over time, we just need to be mindful of the balance, and whether we have an imbalance tipping in favor of breakdown. But as I mentioned, a key player in all of this process is a protein complex within the cell called mTOR. And mTOR acts like a cellular switchboard. It's integrating the signals from nutrients, most especially amino acids, as well as, in fact, most especial among those is leucine, which I'll mention multiple times in this mini lecture, but also it integrates the signals of anabolic hormones, which I've mentioned and we'll discuss in more detail in a moment. But also it integrates the signal from the mechanical stimuli from the actual challenging of the muscles through resistance exercise. So think of mTOR as it's a foreman on a construction site, and the construction site is each individual muscle fiber. It directs the workers to build when materials, nutrients, the blueprints like hormones, and the tools, maybe we would say that's like exercise, are all on site, ready to contribute to the construction. And when activated, mTOR stimulates the machinery that drives protein synthesis. In other words, it will tell the muscle, we've got everything we need, it's time to build. But when mTOR signaling is down or impaired, even in the presence of nutrients or exercise or the hormone signals, the muscle's ability to synthesize the protein and hold on to it and prevent it from getting broken down excessively is blunted. And that's, of course, where anabolic resistance comes in. Now, while aging and obesity are the big two, there is a third contributor that I'm just going to mention now before we get into the big ones, and that is inactivity or just sedentary lifestyle, not moving. Studies on bed rest, like those from NASA, uh, designed to simulate space travel, showed that even short periods of immobility, just like a week, can cause rapid muscle loss, up to 1 to 2% of muscle mass per week. And it does so actually by amplifying anabolic resistance. So these human studies have shown that when you then go in to the sedentary person and attempt to stimulate muscle protein synthesis, it doesn't work as well. So this means in everyday terms that just sitting at a desk job or prolonged inactivity can mimic aspects of aging or obesity, making it a crucial component to helping with muscle mass. The reason this is so important is think about the way the average young individual lives nowadays compared to, say, my generation, where, me getting close to 50 or so. And this is a very, very different lifestyle where kids just sit around more, which is pretty sobering because you think that they may start at even childhood beginning to trigger some of these signals that mimic the process that's happening in their 70-year-old grandparents. Okay, now that we've discussed the origin and me touching on another one, the sedentary living, let's zoom into the big ones, aging and obesity. And let's start with aging because that is the main one. That is, in fact, the aspect that gave birth to the whole idea of anabolic resistance. With aging, there are several physiological changes that converge to impair muscles' anabolic response. One of the most significant is the decline in anabolic hormones. Now, I mentioned testosterone a moment ago, and that's a very relevant one. But it's more than that. Also, growth hormone and one of growth hormone's products, IGF-1, insulin-like growth factor. Just to make that last comment I made clear, where I said that IGF-1 is a product of growth hormone, it is. So growth hormone comes from the anterior pituitary, and it acts throughout the body. So it is itself a signal, just like testosterone is. But growth hormone is unique because it's its own signal, but it's coming from the brain. Most of the brain signals go to somewhere else. Like testosterone doesn't come from the brain, that comes from the gonads, testes, and ovaries. And even then, it is coming because there's a signal from the brain telling it to be released. So growth hormone is its own signal, and it's unique because it's direct from the brain. But also, growth hormone will come down to the liver and stimulate the liver to create IGF-1. And IGF-1 is a very powerful anabolic or building up hormone. Well, all of these hormones are down with age. IGF-1 in particular is a very key activator of the mTOR pathway. In fact, far more than growth hormone. So anyone who is using growth hormone to get big muscles, it's not actually the growth hormone that's promoting the muscle growth. It would be the downstream activation of IGF-1. And when IGF-1 signaling is reduced, however, like it is with age, the muscle's ability to build and maintain protein is compromised. Another issue is just the reduced delivery of amino acids to muscle tissue. Aging impairs insulin signaling, as we've discussed previously. Aging is very much a cause of insulin resistance. Now, it's not a direct cause. There are other factors here. But suffice it to say, if insulin signaling is down, which it is with aging on average, that actually impairs insulin-mediated capillary recruitment or vasodilation. And that means you're delivering less amino acid load to the muscle. And so it doesn't reach the muscle as well. Now, this is important as just a very brief tangent. Few people appreciate insulin's effects on vasodilation, promoting blood flow to the muscles and other tissues. When we think about insulin, we often only think about its ability to induce glucose uptake or its ability to direct the use of various nutrients in cells. But even before insulin gets to the cells of the tissue of interest, say muscle or liver or fat tissue, it's having an effect on the cells of the blood vessel. And again, a primary effect is to induce vasodilation. In fact, there's an entire, pardon another tangent within a tangent, line of thinking that much of how insulin promotes muscle glucose uptake is less so through the direct signaling on the muscle to open up these glucose transporters, and more so a purely function of stimulating a dramatically increased amount of blood flowing to the muscle itself. Now, that might have been an unnecessarily complicated tangent. Just suffice it to say, insulin promotes substantial changes in blood flow to muscle. And when insulin's working well, it expands the blood vessels, promoting greater blood flow. When insulin is not working well, then the endothelium of the blood vessel is not responding very well. The blood vessels stay constricted, and that reduces blood flow. If blood flow is reduced, you're going to, as I stated, and at the beginning of this entire tangent squared, then you are delivering fewer amino acids. The amino acid load is reduced to the muscle. Now, beyond that, with aging still, there's also a shift in signaling within the muscle. Some proteins like myostatin and TGF-beta are signals which inhibit muscle growth, and these tend to go up with age. So you take a muscle biopsy of a younger person, take a muscle biopsy of an older person, you're going to see myostatin levels and TGF-beta much higher in the older muscle. That's a problem, again, because those block muscle protein synthesis and retention. So they also suppress satellite cell activation, which are these little cells that are future muscle cells, just sort of waiting on the sides for their opportunity to come into the game and become muscle cells. Well, they stay there. We aren't activating those satellite cells as well. So muscle regeneration gets compromised. Ultimately, all of these signals come together to tip the balance towards more atrophy or muscle wasting. Now, one of the more compelling pieces of evidence for anabolic resistance in aging comes from a recent study just published in 2024 by Luc van Loon in his lab at Maastricht University. They compared muscle protein synthesis rates in older adults after consuming either an omnivorous meal, in other words, animal protein, or a vegan meal. And both meals were matched for calories and protein content. That is very, very important. So there was the same amount of protein content in both meals and calories, because calories also matter. Fat also matters in this. But the animal-based protein source stimulated significantly higher muscle protein synthesis than the vegan meal or protein source. This finding underscores a very, very important point. Older adults with anabolic resistance cannot afford to rely on inferior proteins. While younger individuals may get away with lower quality proteins, which is to say plant-based proteins, older adults require a higher quality. And a lot of this is they need more leucine. That is that main amino acid I mentioned a moment ago, like whey or beef. All these animal proteins will have much higher levels, but they need more of a push to get over that anabolic threshold. So this is a clear example of how aging muscle becomes more demanding and a little less forgiving. It needs more. Building on that idea, other studies like those examining leucine thresholds show that older adults need about 3 to 4 grams of leucine per meal to hit peak synthesis. And that's almost double what you need in a younger person. But we also need to be mindful of sex differences. As much as I mentioned testosterone a moment ago, Estradiol, the main estrogen, is also very relevant in this. And so women will often experience accelerated anabolic resistance post-menopause due to the estrogen drop, which further dampens IGF-1. It increases myostatin, making just making the individual, the gal, more mindful of some hormone strategies. But it's another reason to look a little more favorably at HRT. People may look at HRT just as with hormone replacement therapy as being relevant to, say, helping with Alzheimer's risk or heart disease, well, also muscle, because estradiol is, in fact, somewhat, albeit less potently, similar to testosterone, a muscle protective hormone. All right, that is enough for aging. Let's shift gears and talk about obesity. Obesity introduces a different but a little overlapping set of challenges. We've discussed previously that fat tissue grows through hyperplasia, which is the multiplication of fat cells, or, well, I should say or hypertrophy, which is the expansion, the volumetric expansion of each individual cell. Now, I do say and because at least at an initial point of fat gain, you're going to have a little bit of both. But then after a little bit of fat gain, it's overwhelmingly in the average individual going to be a matter of almost purely hypertrophy. That's why the increased size of the fat cell matters so much. And as the fat cells become hypertrophic, they begin to secrete pro-inflammatory cytokines like TNF-alpha, C-reactive protein, interleukins, all of them. And these cytokines impair insulin signaling. As I've noted before, inflammation is a cardinal cause of insulin resistance, but they also promote muscle catabolism. And the result of this is a state of some chronic low-grade inflammation that disrupts the anabolic signaling of the muscle, thereby promoting anabolic resistance. And another feature of the hypertrophy of the fat cell, in addition to the inflammation, which I'm going to revisit, is that it starts to promote, it becomes insulin resistant to prevent its further growth. Now, this isn't a lecture about fat cell dynamics, as much as I always have a hard time not talking about that. But as the fat cell gets too big, it starts to promote insulin resistance to stop its further growth. But at the same time, in addition to the inflammation that it's leaking out, which causes insulin resistance systemically, the overall metabolic milieu has changed in a way that I don't want to get into right now for the sake of time, and have indeed discussed previously. But it also further promotes insulin resistance throughout the body. And insulin resistance is damaging to the muscle in ways that go beyond glucose uptake. Under normal conditions, insulin acts as an anti-proteolytic signal. It's an anti-catabolic signal, suppressing muscle protein breakdown. It does not directly stimulate muscle protein synthesis. That is not true, and it has been shown to not be the case in both isolated muscle cells and in whole muscle in humans. So to say that another way, insulin is not essential for the building up of the muscle, for the anabolic side, as much as insulin is an anabolic hormone. Insulin's effect on muscle protein synthesis and muscle mass is more so on the other side, where it is reducing the catabolism or the breakdown. But of course, in insulin-resistant individuals, the suppression of the catabolism is blunted. And so the muscle continues to degrade protein, even in the presence of insulin, when insulin would be attempting to signal the muscle to hold on to it. Now, that's not to say insulin doesn't facilitate some uptake of the amino acid. It does. So insulin helps the muscle pull in amino acid, although it's not necessary for it, but that it stops there. But even still, on that front end, when insulin signaling is impaired, amino acid uptake can be compromised, which can, of course, mitigate some degree of muscle protein synthesis, even if insulin isn't directly involved in that process. But nevertheless, it does make it clear that if insulin isn't working well, you have a double hit where you have some degree of compromised synthesis and absolutely compromised inhibition of muscle breakdown. One other comment on obesity before we mention inflammation a bit more is that obesity leads to the accumulation of lipids within muscle. This is a condition known as myosteatosis. In fact, this comes right back to the hypertrophic fat cell. As it becomes insulin resistant, it's leaking out its fat as free fatty acids. Now, one may say, well, that's no problem. The muscle can just burn those free fatty acids. Muscle loves burning fat. But not if insulin is elevated. If insulin is elevated, but the muscle, the fat cell isn't listening, so it's leaking out its fat anyway, then that fat is forced to get stored elsewhere, like the muscle. Now, I mentioned muscle stores more lipids. Some are more relevant than others. Among these lipids, ceramides, which you've heard me discuss previously, are particularly disruptive. Now, ceramides are simply one of the thousands of different types of fat within every cell of the body. Ceramides are so relevant to conversations of metabolic health because they interfere with anabolic signaling by inhibiting a protein within the cell called AKT. And I mentioned mTOR earlier. Actually, all of what mTOR is doing is related to what AKT is telling it to do. So suffice to say, these signals are getting disrupted because ceramides are acting like some bar that is some rod or stick that's just jamming up the gears or the wheel here. It's stopping things from turning and working. Now, this overlaps heavily with type 2 diabetes, where you have all the glucose amplifying inflammation. Hyperglycemia does result in hyperstimulation of white blood cells or immune-related cells. And we have that ceramide buildup, which starts to create a very vicious cycle. In even young individuals that are obese, we see this, especially in off-season athletes, where they suddenly become less active, they gain fat, and they can have a rapid reduction. In fact, there's a human study showing that in professional soccer players during the off-season, they can have a 10 to 15% reduction in muscle function in just weeks. So some early intervention is critical. Okay, to tie it all together, let's examine some of the last effects here with inflammation. I've already mentioned insulin and its role involving with protein turnover, more so again on the anti-catabolic side. But the inflammation signal is a critical signal in its own right, where inflammation, beyond causing insulin resistance, creates a direct disruption at the muscle. Now, I'd mentioned some cytokines like TNF alpha and C-reactive protein, both of which are coming, by the way, from hypertrophic fat cells, and they can interfere with this signaling. But when they come to the muscle will receive that inflammatory signal. Part of that signal will be the activation of what's called transcription factors. These are master regulator genes that when they're turned on, they're going to go on and turn on a host of other effects within a cell. This includes things like NF-kappa B or STAT, STAT3, which increase the expression of muscle-specific enzymes that tag muscle protein for destruction. So to be clear, you'd have an inflammatory signal, say, coming from a big fat cell, and that tells the muscle cell to start basically tagging muscle proteins for destruction. And as they get destroyed, you're having this dramatically enhanced catabolism where the muscle cell is just leaking out its amino acids. And this is a reason why in insulin-resistant individuals, especially people with type 2 diabetes, you will uniformly see elevated levels of branched chain amino acids. It's not that the branched chain amino acids are causing the muscle insulin resistance, it's that they are a consequence of the muscle insulin resistance. Now, this topic right here introduces an interesting aspect to supplementation with omega-3. Omega-3s are known to be anti-inflammatory. Perhaps some of the evidence that supports the use of omega-3 in promoting muscle growth in humans is because of the anti-inflammatory effects. But to start to wrap all of this up, this is why interventions that improve insulin sensitivity, like resistance training, weight loss, and omega-3 supplements are effective at restoring some anabolic signaling. They don't just improve glucose metabolism, but they can improve muscle's ability to respond to these anabolic signals. Again, both by enhancing the anti-catabolic aspect, so helping the muscle stay where we want it, but also enhancing the responsiveness to the signal. So let's just really wrap up with some practical solutions. Because anabolic resistance is reversible. Even in 70-year-olds, there's evidence to show that with resistance training, you restore some stimulus. And indeed, resistance training remains the most potent anabolic stimulus. If you are listening to this, I'm afraid you are going to need, I can hear your groan from here. You don't want to get up and do something. You have to get up and do something. Changing your diet will not be enough. And the good news is, even in older adults, some high volume or some high intensity resistance training, which is relative. Remember, it's relative. It's not you doing what you did when you were 25. It's you doing what you can do now. But that is the strongest signal. That mechanical loading will activate mTOR more than anything else. Then, of course, protein intake matters tremendously. You want to get leucine-rich proteins, and as the evidence suggests, and as unpopular as it may sound, do not waste your time or stomach space on plant protein. Don't waste your time. That Van Loon study made it very, very clear. Animal proteins are critical in older adults. Young people can get away with these inferior cruddy proteins, although I'd still say, why waste your time and money on this? Focus on animal protein. It is the best to help overcome anabolic resistance. And there could be a case for a multi-ingredient approach. A recent randomized controlled trial showed that combining whey protein and casein, both of which are proteins from dairy, combining that with creatine and vitamin D and calcium and omega-3 improved lean mass and strength in older, obese individuals. So that's the double whammy. They're old and they're obese. So some of these are going to work synergistically. I am an advocate of creatine, and I'm an advocate of vitamin D3. I think both of those ought to be a part of your intervention for improving anabolic resistance. Creatine not only directly activates muscle protein gene expression, the genes that directly feed into muscle protein, but also vitamin D helps, it kind of greases the skids, which is appropriate because it's itself a fatty molecule. Also, there are some other molecules, one called hydroxy beta methylbutyrate, HMB. It's been shown to boost muscle protein synthesis in older adults by up to 20%. And you can also have some other more modest muscle stimuli like these e-stim devices, but they're not going to be as good as lifting weights. Now, one final comment would be things like peptides like BPC 157. There are more and more peptides that are gaining some traction. It's still a very young field, although I think we have reason to be quite optimistic. It wouldn't surprise me if in the very near future we have a host of well-studied, researched peptide therapies that will help with muscle mass, particularly in aging. But of course, ultimately, the best approach is going to be multifactorial, involving resistance exercise, smart supplementation, and nutrition. All right, that's it. Thanks for listening. Until next time, more knowledge, better health. Looking to improve your own metabolic health? Visit insuliniq.com for courses, coaching, consultations, and a 10-day free community membership trial. To dive deep into the science behind metabolic health, become an insider at benbikman.com, where you'll enjoy my exclusive content, ad-free podcasts, live stream Q&A access, and more.